So let's continue with a final presentation. So the speaker is Dr. Roland Ewald. Roland completed his PhD in the computer science at the University of Rostock, where he also worked as a research scientist. In 2014 to 15, he was leading a software development team at a clinical laboratory for genetic diagnostics. And since 2015, he's a co-founder at Limbus Medical Technologies, and at the moment he's the head of the industrial engineering and IT, currently leading the bioinformatics and cloud infrastructure team. And today we'll be talking about how I learned to stop worrying and to love hg38.
Yeah, thanks Yvonne for the nice introduction. I try to keep it short and sweet. I know I'm between you and your coffee break. Yes, I really would like to tell you a bit how you can also start loving hg38 and stop worrying. You may have noticed that we kind of took this phrase from a kind of Stanley Kubrick classic movie, Dr. Strangelove, about people in dark rooms making high stakes decisions under pressure. And you know, whenever a customer comes to us and asks us, you know, guys, we would really like to switch to hg38, what should we do? That we kind of have the same feeling, because you know, it's a tough decision, and it's a decision it's hard to get back from. You shouldn't mess it up. It's complex. There's a lot of nuance. And you know, like if I get this question, I typically have this kind of engineer reflex that sets in. It basically says, well, like, it depends. You know, there's so many variables. So, but of course, that is not helpful for you. So, oh, is it black and white? Anyway. Doesn't really matter. So just imagine the check marks to be green. Let's say in the last years, however, I would say that my opinion about hg38, that it also kind of brings you additional trouble and you have to be very careful in rolling this out, have been somewhat alleviated. So let's say that all the fundamentals are out of the way, because I mean, let's face it, it's not new anymore. It's 10 years old, and that means also that all the reference data sets are now actually available in hg38. For example, Decipher was, let's say, pretty slow in also providing hg38 coordinates. But also GNOME, ClinVar, so you have everything that you need for clinical genetics, you now also have on hg38. And why is that important? I realize that many of our customers mostly think in protein changes and cDNA and like these, let's say medically relevant terms. But from a bioinformatics perspective, this kind of reference genome is super fundamental, because without that, we wouldn't even be able to kind of share data and really compare variants across labs. And so this shift to a new version of the reference genome comes with all sorts of strings attached. But that's another thing that has been clarified in the last years. It's super clear that it's very useful in clinical practice. There are many, many genes that you just can't see on hg19. We've counted this for the most recent NCBI annotations, and it comes in at about 120 genes that you just don't see on hg19, with about 200 transcripts. Of course, this number is also growing. Plus the transcript annotations for hg38 are more recent, right? So NCBI typically does an hg19 transcript annotation only any like 18 months or so, while with hg38 they are more diligent. And still, you know, with all these improvement, there are still legitimate worries that you can have and concerns. And I would, let's say, pick 3 of those that I think are the most valid ones. First is quality issues. So even hg38 is not perfect. There's quality issues that you need to know about. Also, well, it's a big change. It's a change that affects your whole team. So it also means that you have to take time to plan it, and it will require extra work. And third point would be, well, you now have this nice heap of hg19 data, what to do about it, right? So there's this bioinformatics method that's called liftover, which basically means that you recalculate the coordinates and kind of transfer the genomic coordinates of your variants to hg38. But this comes with pitfalls, and it's somehow tricky. So I will give you a few hints about that later on. And of course, let's say the overall problem here is data loss, right? So you really want to keep your data that you collected over the years and your in-house database. And so, yeah, that is often, let's say, a big worry. And you know, if I see this like buzzwords, we want to change something and it has quality issues and it requires extra work, and in the end I might lose data, I'm not a fan, you know. So let's go through each of those slides and see what's going on. The first worry is data quality, and yeah, it's a bit unfair here maybe, but yeah, it's a cute hamster. He's not really to blame though, but there was a nice paper from the Genome in a Bottle Consortium from last year in Nature Biotech, and basically these guys found hamster DNA in hg38. So the hamster might not be at fault, but he is in the wrong place, and fortunately for us, this hamster DNA is only in an alt context, so it's kind of fairly easy to remove. But let's say more problematic is that there were also some larger artifacts in hg38 that this paper pointed out on chromosome 21, so like really clinically valid. And everyone here in this room who does NGS short read sequencing knows if you have like an artifact, a large duplication, it is essentially the same as a pseudogene, right? So it kind of masks the reads because your aligner could align the reads at either place, so it will be discarded, which means you will not be calling variants in these regions. And of course, that's bad. And so we tried to assess the impact of this problem, and we found out that it's 19 kilobases of exonic regions that are impacted by that. And if you take all the RefSect regions, including intronic regions, you clock in at about half a megabase, which is considerable, right? Considering it's 30 megabase exon and so on. This is something that we needs to be addressed. And we did so with our latest release. So no more hamster in the Varvis reference genome, so to say. And we also removed this duplication that the Genome in a Bottle Consortium pointed out. Let's say I consider anyone else switching to hg38 to do the same and encourage you to really, let's say not, I think it's not in the latest patch. You really have to do this on your own for now. Yeah, so with quality issues out of the way, the next thing is, of course, still, if we consider a switch, that takes some work, right? So we were considering, again, using the metaphor that Robin already brought up about needles and haystacks and clinical genetics. We are considering, of course, let's say the way that is the easiest and calmest way for you to do that and how we can support you on that. And let's say we know that the day-to-day life is already stressful and challenging, and we were kind of really thinking long and hard, let's say, how to keep it, the whole process very, very simple. But still, of course, we are really realizing that we are only one tool that you use. So I can only give you, let's say, our perspective on this issue, right? It really depends on the context here. Here I have to say the engineering proverb, right? The process can't be simpler from my point of view. You really have only, let's say, 3 steps. The first thing is you have to check if you are prepared to move to hg38. This implies that you, from my point of view, you have to run production samples on a new experimental workflow. And this has to include really everything. All your different kinds of tools, you may have other bioinformatics tools you are using, all your different kinds of techniques like Sanger sequencing, MLPA, and these kind of things, they have to switch. And also, as Robin pointed out, we have a powerful API. This interfaces informatics, bioinformatics tools on your side maybe. They may or may not be working with hg38. You have to check that, right? And this can take several weeks, to do this diligently. Once you do that, what we recommend, once you think you are ready, I think what we recommend is really have one single fixed state for the whole lab, and not like different teams and so on, because this is, and at that point you would be running 2 parallel workflows in production, right? And it's like twice the complexity. So let's say from our point of view, the easiest thing would be once you think you are prepared, set a fixed date and then validate your new workflow. And as Irene just pointed out, we do support you with validation anyhow, right? So this basically you get by using Varvis as a platform. And to help you with the first step, with this check of preparedness, what we are doing is basically we give you a complete, separate, new, and empty hg38 Varvis setup. So it's basically your lab minus hg38.varvis.com or something. And then you basically can just run trial runs and see how your bioinformatics tools work with the API. Like there's like subtleties like chromosomes start with CHR now, these kind of things. This you just have to know and try out, right? Trying it out is much better than just, let's say, hoping it works. And so then basically what is left here for you to do after you have received our validation documents, so to say, would be to set a fixed date, right? And that sounds kind of doable. Leaving us with the last step, which is basically now you have 2 setups, right? An hg19 setup and an hg38 setup. what to do with the old data, right? You still have this wealth of data, and actually it's one of the core features of Varvis is that you build up your in-house expertise via this variant database. So our variant database stores every variant your lab has ever seen, and this we now have to somehow rescue, right? And there's this bioinformatics technique or method that I mentioned. It's called liftover, but liftover is really tricky. And so sorry, next slide is the one little bit technical slide that I have for you. It's mostly for the bioinformatics people in the room. It's stuff you should, let's say, consider when you're doing this in-house, because I imagine many of you have teams also with in-house variant data. And they are basically, there are basically two things here. The first is there are certain genomic coordinates that are not isomorphic, so to say, right? So if you go from hg19 to hg38 and you go back, you don't land at the same point, right? Which is super confusing. Basically our recommendation here is don't do it. Just go forward, right? Always lift over only from, let's say, an older to a newer reference genome. Go from hg19 to hg38, but not the other way around. Otherwise, you may have variants that have been mapped from other variants, and you kind of goes in circles. This depends on the structure of the, on the mathematical properties of the chain files. There's a paper I can recommend from Ormond and Al, and they basically just brute forced it. So they lifted over every single base in the reference genome and found those positions that are unstable. But well, in the end, you can avoid that by just going one way always. The other thing that is also a pretty nasty gotcha is the normalization issue. There are a lot of tools for liftover, and if you, depending on the tool that you are using, you may or may not have to lift over your variants again. And this is critical, because if you don't do that, if you don't do the normalization again, it could be that you're basically just missing variant annotations like clinvar, because your variant in hg38 at one point now is not normalized anymore because the sequence context changed, right? So you have to normalize it again. Only then you can match it with the annotation data. And the bad thing about that is this happens silently, right? You will not notice it. Everything will work fine. You will just have variants that are not annotated with all the data that you have. That's why it's bad. But good news here, if you do everything right, so let's say what we are achieving is something like 99.5% of the SNVs can be liftovered. We've done this now with about 10, 15 million unique variants, something in that order. So I think that's should be a good estimate. We have done smaller and larger projects for our customers, so that should be fine. And yeah, there's one last thing that I would like to mention here. We are not the only people, let's say, having trouble with liftovers. The GNOMAD consortium also had, let's say a few things that you have to consider. So there's a GNOMAD version 2, this is hg19, and a GNOMAD version 3, which is hg38, but these are not the same data sets, right? And we ran into this recently with a customer who also needed the old data set that is also including exomes, right? If you do rare disease diagnostics, it's really important to have also the exact data, for example, right? These older data sets. And these are not included in the hg38 version. So what we did is basically we are providing now a link from the hg19 version to this specific GNOMAD version, just so that you even can also access GNOMAD, like the hg19 historical GNOMAD in these cases. And yeah, so apart from that, what we are doing is we are giving you your old data as an annotation source. So in Varvis, basically all data like clinvar or your own in-house database are so-called annotation sources, and they give you columns. And we basically treat your old hg19 database as a new database, so to say, that you can always see for each variant, oh, did I find it in hg19 already? What is the significance? Did I leave a comment for the variant, and so on? And since you have your old setup, that would be basically at that point a read-only instance, like a read-only Varvis version, you can just look it up there, you know? So there's this nice, from our point of view, it's a nice compromise between having starting from scratch, with a new pipeline, and having everything on one reference genome, but also being able to go back and, let's say, have more context if you really want to look at the older case. And yeah, with that, I'd like to finish and come back to my worries. So there's no fundamental issues anymore with using hg38 in clinical diagnostics, and let's say I hope I achieved my goal, and even the 3 worries that I pointed out about hamsters in the DNA that you have to mask away, and about the process to use, how to really make the switch by testing diligently and also validating this, and also by doing the liftover of the data are kind of clear to you. And yeah, last not least, yeah, sorry, almost forgot that, but it kind of goes without saying, we do support you every step of that way, because we've done this a few times now and have the internal toolings for that. And the two guys who mostly worked on this internal tooling are Shiva and Rolf, two of my colleagues. So yeah, so just so that you know the faces behind the process that we've set up for that. And with that, I'd like to thank you for your attention. And yeah, if you have questions, I'm happy to answer.
Any questions?
Thanks for a nice talk. Sorry if it's a stupid question. What do you mean with renormalize in this context?
Sorry, I'm always assuming that the variant data is already normalized, right? So we kind of normalize data, like typically, let's say, whenever we have to, you know, that's, so I'm assuming that your hg38 data is already normalized, and I would actually advise this because I would imagine that most of the liftover tools are tested with normalized variants. And what I mean with a normalized variant is, let's say, imagine you have like several T's in one row, for example. Now you have an insertion, right? You don't know which T was inserted, right? Could be the first, could be the last. Doesn't really matter because it's a sequence, right? And for bioinformatics, that's a problem because it means I have like now like maybe 10 ways to describe the same variant. You know, like there could be the T in the first position could be inserted, or the second T, or the third T. Doesn't really matter, right? And so there's like this rule for in bioinformatics that you say, well, on genomics, you just kind of left shift the variant. That's how it's called. Basically, you use the most left, like the smallest index description of that. And that's called normalization. There are a few other rules, but it's a fairly straightforward algorithm. It's not a big deal. So any kind of bioinformatics person can do that, right? But the thing is, or let's say, what is the gotcha is, after liftover, the variant is not normalized anymore, which is kind of surprising, you know. But if you think about it, the structure can change, and there are some corner cases, and then let's say, you could assume that, well, if I'm receiving a normalized variant, I have to put out a normalized variant, but that's not the case. So you just have to have this one kind of due diligence step in between. That's all I'm saying, right? So because it's kind of dangerous if you don't do that, because then you are assuming you have normalized variant and you don't, and that means you would, for example, not see GNOME annotations correctly if the tools you're using assume that you are using normalized variants.
Maybe a second question. I mean, instead of doing this kind of tedious liftover, wouldn't it be easier to just reanalyze the samples with the hg38? Or is this too expensive, too computational, too much work, energy consumption, and so on?
Very good question. Yeah, I think, let's say that's what the GNOME people did. And you see, like, they didn't do this for everything. So they have the sequencing data, but yeah, it takes a lot of work. And even then, you know, like, typically the enrichment kits also change, right? So even in the bioinformatics configuration, then you would have, it's still like not the same quality. For example, if you have a twist kit and you have like the hg19 regions and the hg38 regions, you know, like, the bioinformatics configuration, I mean, you could start from raw reads, right? I mean, I guess that's what you're telling me, right? That should work, but yeah, that is kind of expensive. And let's say we have customers who did this, let's say when they switched fairly early on, you know, like if it's like 100 samples or a couple hundred trios, but everything else is just way too expensive. You know, it's just a cost thing at that point.
Then thank you all for coming. In your interest, stop by at booth 266 for more information. Thank you to all speakers. Thank you, Nadine, for the awesome organization. See you soon. Bye-bye.